Next, we consider integration on more general bounded closed regions. For example, if we have xy plane, the region we want to integrate maybe something like this. So in this case, it may not be possible to carry out integration in the way we have described so far. In such a case, we want to change the variables from x and y to something else. Let's call them u and v. So that the rectangular region in this uv plane corresponds to the closed region in the xy plane. Let's call this region A. So we want to find some mapping. Let's call it phi, capital Phi, so that by this mapping we can transform this rectangular region in UV plane to some general bounded closed region in the XY plane. So that means the image of E by this mapping phi corresponds to the region D. Okay, and we have to make a few assumptions regarding this mapping phi. First of all, this is UV is an injective mapping. And second, we should write this UV as x is a function of u and v, and y is also a function of u and v. So if we write like this, we assume that these functions x of uv and y of uv are of class C1 at least. So that is, these functions are continuously differentiable with respect to u and v. And also, at any points, call u0, v0 in E, so at any arbitrary points in this region, in this rectangular region, we assume that this quantity is non-zero. U times yv minus x v and yu. So this is non-zero. Here's an assumption. Okay. The reason for this will hopefully become clear later. So in other words, if you recall, this is the Jacobian, the determinant of the Jacobian matrix. Okay, so we impose the condition that the determinant of the Jacobian is non-zero at any point in E. So now we want to find a way to integrate this kind of function. And by changing variables, we have a composite function. So that is f after phi of uv. We have f of x of uv and y of Okay, so somehow we want to find a way to integrate this function like this, and we transform this integral in terms of an integral with respect to u and v. So that is something like e and function of this and uv, but this is not true in general. We need something else. So here's the theorem of change of variables. And if we want to calculate this integral in terms of variables u and v, we need this. And this j of uv is the Jacobian, the determinant of the Jacobian. So that is uv and y dv uv minus dx dv and dy du. Okay, so this is the Jacobian, determinant of the Jacobian, and we take the absolute value of that quantity here. So we need absolute value of that to make it positive. So that's how we can carry out the integral by changing variables. So since this E is supposed to be a rectangular region, we can readily carry out this integration by iterated integral. And I will not going to prove this here because it's too complicated, but I will try to explain the meaning of this in a hand-waving manner. Okay, first let's partition the rectangular region E into small rectangular regions like this. So in this way, each small rectangle here in E corresponds to some region, some small region in D, like this. So in this particular example, this yellow region, red yellow region corresponds to this yellow red region in D. And if we consider the integral on D, this can be approximated by the summation, similar to the Riemann sum. So each of these will correspond to like Eij, and this corresponds to Dij. Okay, and f of x ai ci and ai cj and cj times the area of Dij. Okay, mu of Dij means the area of this shape. Okay, AI and Cj are the points here and here. So what this quantity here means is the volume of some solid with the base of Dij and the height of f of xy. So this is the height and this is the area of the base of the shape. Okay, so if we add these quantities over all over all these small regions, then we can approximate this integral. Next, look at the right-hand side of this equation. Okay, so this one can be approximated as this. As the summation again, and f of x, ai, cj, y of x, y of ai, cj times the Jacobian at ai and cj times the area of eij. Okay, so the area of eij is the area of this rectangle here. So if we compare this expression, so these two expressions, we see the difference is here, this part and this part, this part and this part. This factor is the same. So what is the difference here? So this one is the area of this this region. Okay, so this some irregular shape, and mu of eij is the area of this rectangle, and there is a factor, the absolute value of the Jacobian. So if we want these two integrals to be equal, it is sufficient to show that the area of dij is equal to the Jacobian times the area of eij. Let's look at this situation more closely. So we have this rectangle eij here, and this is mapped to this shape dij. Okay, and we are trying to compare the areas of eij and dij. Now, the area of eij is very easy to calculate because it's a rectangle. So that is this length times this length. Okay, so that is ai plus 1 minus ai times cj plus 1 minus cj. And that's it. And the area of dij is a little bit hard to calculate, so we introduce an approximation. So instead of treating this shape exactly, we approximate it by a parallelogram using these two vectors, this one and this one. Okay, so the parallelogram defined by these two vectors would look like something like this. So it doesn't quite fit the shape of dij, but if this rectangle eij is small enough, then the difference here should be ignorable, hopefully. And so we just consider the area of this parallelogram. Let's color it by yellow here. So this shape. Okay, so let's see. Let's try to call this point as qij and qi plus 1j, and this one is qi j So then we have this vector qi plus 1 j minus q ij is x ai plus 1 cj minus x ai cj and y ai plus 1 cj minus y ai cj. So that's the first vector. This one corresponds to this vector. And qi j plus 1 minus qij is x ai cj plus 1 minus x ai cj and y ai cj plus 1 minus y ai cj. Okay, now we consider the Taylor expansion of these quantities. Okay, so x, so it's a first order asymptotic expansion. So this can be approximated as x dx d. So the difference is ai plus 1 and ai, right? So differentiate with respect to u and evaluate it at ai and cj times the difference here, ai plus 1 minus ai. And similarly, yai cj can be approximated as times ai plus 1 minus ai. So this difference can be approximated by this and this. And similarly for this one, x ai cj plus 1 minus x ai cj can be approximated by v. And the difference is between this and this, so cj plus 1 minus cj. And similarly, y v. J plus 1 minus cj. Okay. So let's define a couple of vectors, and let's call it u as consisting of this and this. So let's write dx du as x subscript u. So x u ai cj times ai plus 1 minus ai and yu similarly and another vector v x v cj plus 1 minus cj and y 1 minus Cj. So these two vectors approximate these two vectors respectively. Okay. Now, so we have a parallelogram defined by these two vectors u and v. And if you recall, the area of this parallelogram is given by this times this minus this times this, right? So the area of this is the area is given by xu aicj times ai minus plus 1 minus ai times this one yv, so this one icj cj plus 1 minus cj minus this one times this, or in any order. So xv ai cj cj plus 1 minus cj times yv ai cj and ai plus 1 minus ai. So that is equal to, so this is equal to xu aicj times yv aicj minus xv aicj times yu actually aicj times ai plus 1 minus ai times cj plus 1 minus cj. So this part is the area of eij. And this part is the Jacobian. Oh, wait, by the way, we should put this modulus to make the area positive. Okay, so we have this equality. And after all, this is an approximation of the area of dij. So we have some intuitive understanding of the equality between these two integrals, this and this. So if we change variables, we need the Jacobian. Let's see an example. Consider the region defined by these 4 lines. So the region bounded by these 4 lines. So let's try to visualize this. And x and y. So this one, it's a line passing through the origin, and this line is parallel to it. Let's see. 2.5, so it's parallel, something like this. And this one, it's a line passing through the origin like this, and another line parallel to it and passing through the intercept of 5, so something like this. So you can see that this line, these lines and these lines are perpendicular to each other. So actually this is a so the region defined is this part. Okay. Actually, this is a square, if you can check. So let's see, consider, let's call this region D, and let's try to integrate a function x plus y on this region. Okay, and to do that, actually this is, if you can divide this region in a smart way, you can just carry out this integration. But here we try try a change of variables. So let's define x of u v as 2u minus v, and y of u v as u plus 2v. So how do we come up with this change of variables? That's an interesting question, and you should think about it. So given these four lines, how can we come up with this change of variables? But if we do this, this integration is greatly simplified, because if we define e from 0 to 1 times 0 to 1, then this transformation maps this region to the region D, defined by this. Defined by this. Okay, so we can change the variables like this, and we can integrate on this region with respect to u and v. So this integral is equal to, oh, wait a minute, we have to calculate the Jacobian first. So the Jacobian here is x u v and y u v and x v u v y v u v. So let's differentiate this one with respect to u. You get 2. With this one with respect to u, you get 1. This one with respect to v, you get -1 and 2. So the determinant is 2 times 2 minus 1 minus 1. So that is 5. So the Jacobian is 5, and it's positive, so we just carry out the integration. That is, so x is this, 2u minus v plus, and y is this, u plus 2v. And the Jacobian is 5, and du dv. And we can integrate by iterated integral. So that is from 0 to 1 and 0 to 1 and 3u plus v. Let's try to integrate this. So if you integrate with respect to u, you get 3u squared over 2 and vu. And that is 3 and v. 1, and we get, wait a minute, we need 5 here, don't forget 5. And let's see, so 3 and 1 over 2. So that is 4 over 2, that is 10. So that is the result. So how did we come up with this transformation? And here's the trick. In general, if we have a parallelogram, like let's see, x and y, like this. So let's say this is AB and this is CD and this is A plus C and B plus D. And this is the origin. So if we have a parallelogram like this, then we can make a transformation like x of uv equals to au plus cv and yuv and bu plus dv. So if we define this change of variables, then we can map this square from 0 to 1 times 0 to 1 into this region. So in this example, if we calculate these intersections, so this point has the coordinate, you should try to calculate this 2, 1, and this point would be negative 1, 2, and this point is 1 and 3. Of course, this is the origin. So we can apply these formulas, and so this would be A, B, C, D. So A, B, and C is negative 1, and D is 2. So in this way, we could transform this region into this region. So why does this work? It's actually hard to understand. So if we have these two vectors, this vector and this vector, then we consider the linear combination of these vectors. So that would be so xy. Let's write this way as a column vector. So the first vector is AB and linear combination. So the coefficient, let's call it U, and another coefficient C, D, and V. So the vectors expressed as this linear combination can express this parallelogram if U and V moves between 0 and 1. So if you move, let's fix value of V, and so that will be somewhere along this line. If we move U from 0 to 1, that will move 0 to 1 like this. So when U is 0, it's somewhere here. Let's try to use another. When U is 0, it's here. When U is 1, it's here. Okay, and if you change the value of v, then when v is 0, it's here, and when v is 1, it's here. So as a whole, if we move u and v anywhere between these intervals, then it covers the entire parallelogram here. And another important change of variable is the polar coordinates. In 2 dimensions, it's this, r and theta. R cosine theta and r sine theta. So this change of variable is very common. And the Jacobian is this. So differentiate this with respect to r, we get cosine theta, and differentiate this with respect to r, we get sine theta, and r sine theta and r cosine theta, that is, so cosine theta times r cosine theta, we have r cosine squared, and minus here, so plus r sine squared theta, which is r. So the Jacobian is just r. It's easy. Let's see an example that uses the polar coordinates. So let's say the region is defined as non-positive x and non-negative x and non-negative y, and x squared plus y squared is less than a squared, where a is positive. Okay, then we want to evaluate the integral on this region of this function. As you can see, x squared plus y squared is the distance, square distance from the origin. So it motivates us to use the polar coordinates. So if we use the polar coordinates, this, and we have this dy dx part, dx dy part is like r dr d theta. So this part is, this r comes from the Jacobian. Okay, and of course a x squared plus y squared in terms of the polar coordinates is just r squared, right? So this is r squared and r, and dr d theta. So it corresponds to some region in the polar coordinates. Let's call it E. But here we have these conditions. So if we visualize this, that corresponds to this quarter of the circle. So in terms of the polar coordinates, then r is less than or equal to a, and theta is between 0 and pi half. So this integral becomes from 0 to a and 0 to this, and r cubed d theta and dr. But this integration, this integral does not contain any theta here. So we can just integrate over theta. That will be to pi half, and from a to 0 to a, and that is r to the power of 4. So that is pi a fourth and 8. And that's it.